This is Unit 6E. It deals with motors. But to begin with, more generally, we want to see the wider context of this, and that's what this slide is about. We've got the motor effect here, the essence of what's happening in a motor, and that is we're turning current into motion. That's what a motor does. And we can see also on the right hand side that motion can be turned back into current via the dynamo effect, and this is what a generator is. Dynamo effect is at the heart of electromagnetic induction, but we'll stick with dynamo effect. Dynamo is also known as a generator. So that's the big picture. Let's look at the detail. Now, one of the reasons why this is a tricky idea is that it deals with two invisible things. Firstly, magnetic fields, which we can't see directly, and then current, which is the flow of electrons, which we also can't see directly. So hopefully animation will help us in this case. So we've got an AC supply here, an alternating supply, sending electrons one way then the other, and we'll see in a later image that this is actually creating, or it creates, a magnetic field around the wire that interacts with the magnetic field of the permanent magnet, and that causes the force. So that's why this is moving up and down. If we want to predict or understand which direction the force will come, we use Fleming's left-hand rule, seen here. So our first finger points in the direction of the field, our second finger in the direction of conventional current, which remember is the opposite of electron flow, and then our thumb, our strongest digit, will point in the direction of the force. Over here we have effectively the opposite. We have Fleming's right-hand rule. It's the same idea, but it just has the opposite effect. So here we've got the motion coming in. So we've got some kind of device here, some kind of gripper, moving this coil up and down through the magnetic field, and that creates our alternating current. But big picture, in both cases we're dealing with a magnetic field, and in one direction we're turning motion into current, and the other current into motion. So let's look at a motor in a little bit more detail, but trying to hold that image in our head, that if we have wire here, so going in, well, let's have a look over here. So going into the screen, we have the right hand grip rule. So we point our right hand thumb and our fingers curl round, and here we've got the magnetic field around the wire coming out of the screen. Over here we've got a little bit more detail about the interaction. So we've got two magnetic fields, one from the wire, one from the permanent magnet, and as we know, magnets can repel, and we've got our force here. So this is a coil shown in cross section. So the wire starts here, and as it comes down it interacts, and we get this force and therefore motion. We can see that the permanent magnets are arranged in such a way that they create what's called a radial field. So the curvature here creates a radial field, and that means that the wires are always or maximally cutting through those field lines at 90 degrees, or as close to as is possible. Now obviously when it gets to the top, once it's pushed out, there is no more repulsion, so that's why the current has to change. So we can see every time it gets to the top or the bottom we have this change. Now if we have AC going in, that's no problem, but if we have DC we have to effectively create AC, and that's what this thing here, the split ring commutator, does, and we can see one in action here. So we've got DC, direct current coming in from the side, and this means that this direct current flows one way or the other depending on how the contacts are at that particular point in the cycle. This is obviously simplified. This is a more realistic situation with the motor, so multiple coils, this makes for a smoother rotation. So motors are everywhere. You'll have more than 50 in your house, incredibly useful in lots of situations. Here we have just one example.